I'd like to welcome people to our webinar for workshop instruments, science instruments, the first one, and give you a few ground rules. My name is Charles Swenson from Utah State University. I am the Associate Chair for the Small Satellite Conference. And today we have opportunity to have a panel of the presenters. You can go see their papers on the on-demand cast for the conference. They will be here. We will give them a minute to introduce and give a summary of their papers, and then it will be open for questions. When you're ready for questions, you can find down on the bottom of your screen on the right side a Q&A tab. Please use that Q&A tab, bring it up, and type in questions that you would like to ask any of the members of our panel. I'd like to introduce the moderator for our session today. It's Dr. Shannon Stratum. She is the group supervisor for the Environmental Dynamics Test Lab at the Jet Propulsion Laboratory, JPL, and is the project manager for RAINCube, which is a 6U CubeSat mission currently moving into extended operations. Dr. Stratum previously worked on JPL CubeSat mission Marco and RACE, and she currently serves on the AIAA Small Satellite Technical Committee as the Technical Affairs Committee subcommittee lead. Today we have a number of people on our panel. I'm going to just briefly share my screen to show you the panel and papers that we have. These are our panelist members, and I will let Shannon introduce our panelist members and give them a moment to summarize their papers. And at this point, I'm going to turn our webinar over to Shannon. Thank you.
Hello, thank you. Okay, it says I cannot start my video because the host has stopped it. I'm just wanted to give you that information there. Oh, here we go. Start my video. Okay, great.
Michelle.
Okay, hi. Hello, everyone. Thank you for joining this workshop session on instruments and science. Our first speaker is Rico Fausch from the University of Bern. His topic was CubeSat TOF, planetary atmospheres analyzed with a 1U high performance time of flight mass spectrometer. So Rico, I'll hand it over to you.
So thank you for introducing me. Indeed, we designed a time-of-flight mass spectrometer which fits into one unit and with which we can analyze planetary atmospheres. I'm a postdoc at the University of Bern, where I design mass spectrometers to investigate celestial objects and study the results of them. Now, during designing a mass spectrometer in a 30 centimeters of class, or actually two, the NIMPEP JUICE, which will visit the Jupiter's icy moon, and a mass spectrometer for the Lunar Resource mission heading to the south pole of the moon, I realized that those mass spectrometers are still too big in size. 30 centimeters is small, but it's still quite bulky. So we decided that we need to further reduce the source, the ion source, and the ion optical system of our instrument. While doing so, we really focused on maintaining a high sensitivity so that we have high performance in the instrument, and by accepting a moderate level of ion optical resolution, mass resolution, so that we're still able to analyze heavier noble gases such as xenon and krypton. Now, this is important to be considered for not only analysis in the terrestrial exosphere, but also when we want to analyze planets like Venus or Mars, where those isotope ratios lead to scientific breakthroughs, basically. Yes, thank you.
Thank you, Rico. All right, and just a reminder for all of our participants, you can submit your questions in the Q&A box. And if you have a specific question for a presenter or topic, just make sure to note that in the field there. So Rico, I do have a quick question for you. So my experiences with trying to miniaturize instruments is you often have to compromise somewhere, right? You know, in order to get everything to shrink down to the volume and the mass and the power constraints within our SmallSat and CubeSat platforms, you're going to compromise somewhere, often in performance. And you gave some great examples of current instruments. So I was curious how they compare and where you ultimately needed to compromise somewhere to get the size down to what you needed.
So what our ion optical system is has a energy tolerant ion source. So this means that we can apply it directly in orbit, but we can also apply it in a vacuum chamber. Now, the typical mass resolution of the 30 of the centimeter class of instruments, of the big ones, they have mass resolutions of about 1,000, let's say. And we shrank this down to 300. We accept this. And we also accept a higher power consumption when compared to other instruments in the 10 centimeter class, if you want to. So nothing is for free, as you said, but I think it's really important to maintain a high sensitivities because we really want to do science. We don't want to do technological demonstrator instruments. And this is why we focus on this, but we surely lose power and mass resolution.
Great, thank you so much. Okay, we're going to move on to our next presenter, which is Andre Czerny from MIT. And his topic is environmental testing of the CubeSat laser infrared crosslink CLIC-A payload. Andre?
Yeah, hi everyone. My name is Andre Czerny and I'm with the MIT Star Lab, where we do a lot of experiments and tech demonstrations in the area of astronomy, communications, as well as weather sensing. And in my presentation, I focus on our recent payload, which is called CLIC-A. And CLIC-A is a kind of a tech demonstrator to verify some of the key technologies needed in miniaturized optical transceivers for CubeSats. And particularly with CLIC-A, we're hoping to demonstrate two features of these miniaturized optical transceivers. And that's a fine steering solution based on a MEMS fine steering mirror and the transmitter optoelectronics, which are scalable, and we hope to use them in also our follow-up CLIC-BC payloads. So I'm happy to answer any questions.
Great, thank you, Andre. Yeah, so in your talk, you talked a bit about laser safety and how you've got to prepare when you test this instrument. And I was curious, what class laser is CLIC-A?
Oh, it's a class 4.
It is class 4, okay.
It's an infrared and very high power, so that's the worst of both worlds.
Yes. Yeah, I worked on an optical comm instrument in the past, and that was always very tricky, was making sure we had all the right safety protocols in place. So has that been particularly challenging to set everything up for your test and staying within the typical schedule and budget constraints of our programs?
Yeah, it has been tricky. I think also in particular because maybe there are not even many procedures ready for these kind of applications yet. For example, the FAA was kind of difficult to work with to kind of explain even what we're trying to do. But after all, yeah, we managed to get these procedures, and with a remote enough location, it's been much easier. But I imagine in densely populated areas, it's probably gonna take more time to get these permits.
Yeah, definitely. Okay, thank you so much, Andre.
Thank you.
Okay, and our next presenter is Robert Wright from the University of Hawaii. And the topic is HiTi, High Spectral and Spatial Resolution Thermal Infrared Imaging from a 6U CubeSat. Robert?
Sorry. Yeah, so the HiTi project is basically to launch a 6-unit CubeSat, which will acquire high spatial resolution, high spectral resolution, long-wave infrared spectral data. The motivation for the project is since ASTER was launched in 1999 with 90-meter spatial resolution with 5 long-wave infrared bands, it's kind of remained the state of the art for scientists who want to study the chemistry of Earth's surface and atmosphere. EcoStress was launched recently, has 5 bands. So the focus of the project is to see whether we can increase that spectral resolution by a factor of 5, so to 25 spectral samples between 8 and 11 microns. Keep the spatial resolution, so we're aiming for a 60-meter ground sample size, and demonstrate that we can do emission spectroscopy from space from the 6U format. Less than a minute.
Very good. Thank you very much, Robert. Okay, so let's see. I actually did have a question working on RainCube. Thermal was always a big challenge for us, making sure we could expend the heat that was coming from our instrument. And I noticed in the talk that that's also a challenge for HiTi, that you expect to collect data from most of the orbits, but you might have to turn things off or stop collecting data to protect the instrument. And I was curious, what is the approach there? Is there some sort of built-in fault protection in the payload or maybe in the spacecraft to kind of keep eyes on thermal sensors and maybe powering things down? Or what's the approach there to maintain safety of the instrument during operations?
So a couple of things. So staggered operations, we can't switch everything on at the same time. So we have the payload, which uses a lot of power. We have a highly capable onboard computer, which does the data reduction from level 0 to level 1. And then various other things. Now, if we turn all those things on all at the same time, then things start getting rather hot. The main temperature limit is actually the heat rejection temperature for the cooler. So, the hotter your house is during the summer, the harder your fridge has to work to do the same amount of cooling, right? So we've done an extensive amount of modeling, and there are some periods during the orbit when our heat rejection temperature will get close to the limits of our margin with respect to can the cooler actually do enough work to drive the FPA to the operational temperature. But that's only for relatively few small periods of time during the orbit. Our thermal modeling indicates that for most of the orbit, we'll be able to require data, turn the cooler on, drive the FPA down to its set temperature, and acquire data while still retaining a healthy margin on that, the temperature of the cold sink, if you like.
Okay, thank you very much, Robert. All right, and our next speaker is John Krysmanek from UMBC NASA Goddard. And the talk is VTXO, the Virtual Telescope for X-ray Observations. Go ahead, John.
Hello, everyone. So hopefully you can hear me. Yes, so I'm the PI of VTXO. And so what VTXO is actually made up of 2 formation flying spacecraft. One, a 6U OpticSat that has a special kind of optics called phase Fresnel lens diffractive optics. And then another detector sat class, which is ESPA class, that has an X-ray detector, X-ray camera, and then also precision star tracker. And these 2 formation fly in a precise arrangement leading to a 1-kilometer X-ray telescope with about 50 milliarc seconds angular resolution, which is an order of magnitude better than the current state of art given by Chandra. So VTXO was chosen in 2018 as one of the NASA Astrophysics Small Sat science studies and was developed under that. And as I said, the one interesting thing about this is that it turns out that highly elliptical orbits are very beneficial in terms of holding the formation. So we baseline a orbit that was similar to the Falcon, that was done for the Falcon Heavy second flight, 90,000 kilometer altitude apogee. We go into a 200 kilometer, then perigee in that orbit, and then we boost. It only takes 40 meters per second delta V to go to 600 kilometer perigee. And then in that orbit, we can hold that formation for plus or minus 5 hours around apogee on a specific astrophysics target, and therefore image for 10 hours per orbit. And then we lead to about approximately almost about 260-day mission, or anticipated right now 200-day science mission. And just also to say that my colleague Kyle Rankin has a paper in it too, talking about orbit optimization for doing this orbit, not for much for the formation flying, but how to get from the perigee to the formation, where we potentially can have maybe a factor or two of fuel savings, and therefore an extended mission life. So I think that should be it. And I'll entertain any questions.
Thank you, John. Yeah, so I was curious, with the formation flying, what tolerances can you accept there to still meet your performance requirements?
Right. So we come, so basically what it is, the formation is held kind of loosely coming out of perigee with about a 20-meter separation just to save fuel, to minimize the disturbances. But once we get in formation, we have to hold it to plus or minus about 5 millimeters control. That's to get the basically spot from the optics on the X-ray camera. It's about, I believe 4 centimeters on the side is the current X-ray camera sensor we're using. But then we need the knowledge of at the level of about 250 microns, these are 3 sigma, to hold that formation. And these were done in the study with, we had literally, I had 3, if not 4 groups doing the GNC and the flight dynamics, and one ended up doing it with this high fidelity simulation. You see the results there where he ran it 400 times, varying the parameters naturally and leading to the fact that this formation holding was robust. So it's very exciting. That was one of the exciting things I think about the study, is to demonstrate that, it was a closed-end study, that this formation flying potentially can work. And even we have, with the components we chose, some downlink even at apogee to ground, it's not much, and some decent knowledge in terms of GPS, even going around how decent is it, level 100 meters or so, a few hundred meters. But at least when you're doing this formation in such a highly inclined orbit, you pretty know where everything is in case something happens and you have to recover. But and again, this is a step in the direction. We're using very small lenses, small being 3 centimeters. In principle, you could talk about making meter-sized lenses. You would need a larger focal length. The focal length equation is linear in kind of the minimum feature sizes that you can do, and you can only do so much. But in any event, you could talk about doing in the X-ray. So again, this is in the X-ray band. I should have said that 4.5 keV to 6 keV. You could talk about making a milli-arcsecond or even a micro-arcsecond angular resolution mission in the X-ray or gamma rays with this procedure, but with larger formation, a longer formation.
Okay, great. Thank you so much, John. Okay, and our next speaker is Simone Simonetti from Argotec, and his talk is on LISIA on DART mission, an asteroid impact captured by Italian small satellite technology. Okay, Simone?
Hello everyone. So I am Simone, the system engineer of LISIACube. LISIACube is an Italian sponsored, a CubeSat, a 6U CubeSat sponsored by the Italian Space Agency, and that will fly with on DART mission, with DART mission. And LISIACube will be released 10 days before the DART impact on the Didymos asteroid. And prior to the release, it will perform a maneuver to perform correctly the flyby to the Didymos system. And during the flyby, LISIACube will perform an autonomous navigation to track the asteroid, and will take several pictures of the impact site. This picture will be used then from the scientific community to understand better the behavior of the impact and also the deflection of the asteroid with the kinetic impact of DART. And in order to achieve these mission objectives, LiCioCube has two payloads, optical payload. The first one is a narrow field of view to take a detailed picture of the impact site. And the other one is with a wide field of view to take an RGB picture of the asteroid. So that's more or less the mission. And I am very happy to answer to any question. Thank you.
Thank you. So in your talk, you mentioned a 15-month unpowered cruise to the asteroid. And that stood out to me as something that could be incredibly challenging, you know, to have your sensitive payloads just survive without power, heat. So what, I guess, what are the challenges there from your side, and how much say do you have with the DART mission to make sure your payloads are protected during that?
Okay, yeah. For this mission, we designed an external battery charger to power the CubeSat while it is during the cruise phase, and to power also the heater to keep the CubeSat inside the survival temperature. And we also perform battery charging of the CubeSat prior to the deployment, 2 or 3 days prior to the deployment. So we are directly connected to the DART spacecraft, so we can manage the power and the thermal problem during the cruise phase using this external battery charger.
Great. Thank you so much, Simone.
You're welcome.
Okay, our next presenter is Rafael Guzman from Satlantis, and his talk is in-orbit demonstration of the ISIM 170 optical payload on board the ISS.
Thank you, Shannon. Hello, everyone. My name is Rafael Guzman. I'm the CTO of Satlantis, a company specialized in state-of-the-art cameras for the new generation of microsatellites. You may have seen from my talk that our premier product is ISIM, the integrated standard imager for microsatellites, and it is the only camera currently available in the market that can observe simultaneously in visible and SWIR bands with unprecedented spatial resolution in multispectral mode, all the way from 450 nanometers to 1,750 nanometers. It is also a camera that was designed to track irregular linear structures on Earth. For example, coastlines to monitor plastic contamination or smuggling activities, pipelines, oil and gas pipelines to prevent thefts or to detect methane leaks, and borders for safety and security. So there are 3 key innovations that I wanted to briefly summarize here of our design. The first one is super resolution. So our camera is diffraction limited, and we can use super resolution algorithms to go a factor of 2 or 3 better than the actual diffraction limit given by the size of the lenses. This is something that we have already demonstrated in the current flight model of our camera. We have the International Space Station, where with only 150 millimeters aperture, we were able to resolve objects as small as 80 centimeters on the Earth's surface in the visible. The second innovation is multispectrality without the loss of a spatial resolution. So we can put as many bands as we want, and then our algorithm will always maintain the same spatial resolution. And finally, the third one is agility, because our camera can take images both while the satellite moves along the orbit and across the orbit. And we're going to demonstrate these 2 innovations next year in another flight with the Air Force Research Lab to the International Space Station. And finally, just to finish, that we have 1 commercial contract for an oil and gas company in Texas in 2021 with the European Space Agency in order to demonstrate the full commercial potential of the camera. Thank you.
Thank you, Rafael. So I had a question actually about, so I understand that in order to resolve this resolution that you need, you use a lot of AI algorithms. And I was curious how do you go about creating those algorithms? Is it some sort of machine learning? And then how do you validate it? How do you validate that those algorithms are doing what you expect them to do and need them to do?
Yes, I'm actually a professor of astrophysics here at the University of Florida. And what we did is to apply exactly the same technique that we applied to the Hubble Deep Field, the deepest image ever taken of the universe, but now to Earth observations. And it consists of taking many different images of the same location on Earth, so that you can sample very well the point spread function, and then you register QUAD, and in the process you increase your signal to noise and you reduce the spatial resolution. The way that we validated it was both in our labs with a target for the spatial scales, in which you can demonstrate that you can go much finer detailed in your target for the spatial resolution. And of course the proof is in the pudding, so the best thing that we could offer is the resolution of a factor of 2 better than the nominal diffraction limit of the camera, this time from the ISS, when we were able to resolve the blades of a helicopter on the ground. That is 80 centimeters.
Great. Thank you so much, Rafael.
Thank you, Shen.
Okay, and our last presenter today is Jona Petri from the University of Stuttgart. And his talk is the stereoscopic meteor observation, determining satellite bus and formation parameter requirements.
Okay, hi everyone. It's great to take part in this webinar. So I'm Jona Petri from the Institute of Space System at the University of Stuttgart. And we are planning a joint mission together with the Technical University in Berlin. And we want to do a formation of 2 small satellites dedicated to the observation of meteors. And the reason we are using 2 satellites is that we want to observe the same area with the 2 camera system. And this way we can determine the trajectory of a meteor, which we observe from both satellites. And we now have the question that we need to analyze the formation of the 2 satellites in order to optimize the scientific output. So we set up a simulation in order to answer basically 2 questions. The first is regarding the satellite formation. So which would be the ideal formation for the 2 satellites in regards of distance and orbit. And the second question we need to answer is which requirements do we have for the satellite bus in terms of the knowledge and attitude of the satellite, because this also influences how good we can calculate the trajectory of a meteor. So we set up a simulation using a trajectory algorithm and simulated different orbits, satellite distance, and meteor properties. And what we found out is that the satellite distance has a huge influence on the trajectory accuracy. So we need to set the satellites in a specific distance to reduce the error we get on the trajectory. Regarding the satellite bus parameters, it is really important to have a good attitude knowledge in order to reduce the trajectory error. Yeah, thank you.
Thank you, Jona. So I had a question. It sounds like you've decided 2 satellites. You need 2 satellites to get the measurements. And I was wondering, is there any benefit to more satellites, or does that just complicate things and doesn't really give you a lot of bang for the buck?
First of all, it would make it certainly expensive. So this is a reason not to do it. But a reason to do it is we would get more coverage, and we would increase the chance to observe a meteor from 2 satellites. So we need definitely 2 to get the trajectory information. And if you use more satellites, we could certainly enhance the accuracy we get from the data. And we would increase the chance of actually observing meteors. So this would be a good thing, but yeah, it makes it more complicated to calculate a proper formation. And of course, it also is a university mission, so we can't really do more than 2 satellites. But it would be great in terms of the scientific output.
Great. Thank you so much, Jona. Okay, I think now we're gonna turn it over to the audience Q&A. I do see there's been some activity, some questions, even some panelists have started to answer them, but I do wanna ask them verbally and have them address them verbally so everyone can can hear it and get the responses. So this one is for Rico on CubeSat TOF. Is there already a flight opportunity for your program? And if so, can you give some more information?
We have indeed established a mission. We are awaiting funding decision here. The mission would consist of a constellation of 2 CubeSats. They will have one an elliptical orbit, one an SSO orbit. This would allow us to measure the exosphere at different heights. And this is really important to do so because we really want to know the atmospheric escape rates of Earth. And to do that's why it's best practice to do it in an elliptical orbit. I saw other presentations here and in the past having circular orbits, and there you don't have these very measurements at different heights, and this is what we try to do. And of course, if you think it would be a good opportunity to give us a ride share, we're happy to team up with somebody of you.
Great, thank you, Rico. All right, another question. I believe this one is for Andre, for Click A. Do you foresee the use of laser technology to receive, transmit to space internet satellites in order to uplink, downlink in a mesh network, for example?
Yeah, that's a great question. So I think for these large internet constellations in particular, the direct uplinks and downlinks to a user are probably not the best choice because for internet access, the link availability needs to be extremely high. However, I think where our lab has done some research on inter-satellite crosslinks, and we have proven that in large constellations, having crosslinks can improve the throughput through these constellations. And also with inter-satellite crosslinks, the lasers don't have to deal with the atmosphere, so they're much easier to implement. So I see that as a more near-term application for these large constellations.
Great, thank you, Andre. Okay, I think we had, let's see, I'm going through the Q&A panel. This one would be a good one for John on VTXO. So you mentioned let's see, in your talk, you mentioned the extension of this mission concept to precise imaging in the gamma ray energy bands. Can you comment more on what this extension would entail?
Okay, so it depends. It's how the phase Fresnel optics work. These optics work across the electromagnetic band. Matter of fact, if you go back to the original one, they go back to Lord Rayleigh in the optical back in the 18th something. But they work by changing the phase of the radiation. So in the X-ray, it's given by the index of refraction decrement. And similar for going through gamma rays to the point where you end up having issues with, say, Compton scattering or pair production. So we could argue that it works fairly well to probably have the order about 1 MeV. And so then the equation that we have, that lens equation holds, where you have then is you tailor the profile of your lens for the appropriate phase change for that energy. It depends upon the material and the energy. And then the lens equation gives you the spacing. So the lenses in principle are the same, although they look different. The profiles will be slightly different, but in principle it's the same thing. So when we're talking gamma rays, we're talking of something like 511 keV from electron-positron annihilation, for example, or other nuclear gamma ray lines. But you end up going to have probably a longer focal length too, because you can see what the focal length equation is, and depends how big your lens is. So that's the impact.
Thank you, John. Okay, let's see. We have a question for Raphael for ISIM, and that's what kind of IR focal plane does your system use?
Yes, so we're using for the SWIFT channel, we're using the latest generation of the indium gallium arsenide detector. Right now it's about 1200 by 1000 pixels. And for the visible part, we're using CMOS detectors. We have been using so far the CMV-12000, but now we're moving into a larger area detector with a smaller pixel size.
Thank you. Thank you, Raphael. Okay, let's see. Another question we have here. This one's for Yona. Let's see, will the satellites operate in the asteroid belt?
No, we are planning a low Earth orbit mission. So we are gonna aim for a 300 to 400 kilometer orbit. And the reason for this is the further you go away from the Earth, the more complicated or the lower the signal from the meteor. So the meteors occur at a altitude of about 100 kilometers. So we need to be close to the Earth.
Great, thank you, Jona. And this actually brings me to a general question, since Jona mentioned low Earth orbit and complications of operating beyond that, especially for CubeSats. So general question for you all, do you think your instrument could survive and operate beyond LEO for, say, planetary missions? And if so, maybe give us a little bit more details there. So how about Rico? We go with you first.
Well, the ion optical system, of course, will, because there are just a few plates of metal. But the electronics indeed needs to be customized to the mission. But we foresaw in our design process that we are able to swap components from cheap COTS parts, which we will use in LEO, to the high real parts, which we then can use on deep space missions or when visiting Venus and probably Uranus or Neptune. When we are deployed on a flyby. So this is foreseen, although we have to say that it's not usable to put the exact same satellite for LEO to send it to Venus, for example.
Thank you, Rico. Andre, for CLIQ-A, how about you?
Yeah, I think that would depend a lot on the radiation environment and wherever we would go. CLIQ-A has been built with a lot of commercial off-the-shelf components to save cost. So some of these are not radiation hardened. So probably these will need to be replaced, for example, the camera or the optical amplifiers.
Thank you. Robert, for HiTi.
Yeah, no reason why not. I mean, we've been using radiation tolerant or designed radiation hard parts for the whole spacecraft. I mean, you know, yes, usual environmental considerations accepted. I guess one thing is data rate, right? The further out you go. So we've already been dealing with that a little bit. I mean, our level 0 data rate is gigantic because it's an imaging interferometer. So we're already doing onboard processing to go from level 0 to level 1 with an exceedingly limited data rate. I guess the next thing would be to go from level 1 to level 2 and then just send back the science products themselves rather than the level 1 product.
Thank you, Robert. How about John for VTXO?
Actually, I mean, for the formation flying, it'd be nice to get away from these pesky things called Earth and gravity wells, right? Because you're adjusting one orbit to a pseudo orbit. We're actually in high HEOL orbit, right? Because we're at 90,000 climate perigee, or excuse me, 90,000 apogee, and so we're radiation tolerant already. The issue is that depending upon where we are, the previous speaker brought up the COM issue. That's going to be a big issue, getting things down if we're further away from the Earth. The other one too is depending upon where you put this. Say you want to do something a little bit further from the sun, then you have a power issue because their solar panels are sized for a certain power at a time. But I mean, for cislunar or even lunar orbit, something like that, or even Earth drift away potentially could be good for this type of mission. You can hold the formation longer. You don't have to make and break. You could just hold for a good portion of it till you repoint.
Yes, thank you, John. And let's see, Simone, I know you're already going far out, but what maybe challenges have you particularly faced given you're going outside of video?
Yeah, there are a lot of challenges, but we designed from the scratch the avionics of the platform, starting with the idea that we have to fly in deep space environment. So we designed our platform for deep space application, and we are using our avionics that we developed on house, and we are following several QA and PA processes to do this, and we qualify these avionics for deep space application next year with the DART mission, and it will be our first flight in deep space. But we had a lot of challenges to achieve it in a very small space, because we have to use space grade component, but we do not have a lot of room to place them to the avionics unit. So it's a challenge.
Thank you, Simone. Raphael for ISIN.
Yes. So the current camera that we have has been designed for low Earth orbit, and the optomechanics actually are rad hard, so they will do very well. But the electronics are very much based on commercially off the shelf, even though we have redundancy. Having said that, for the next model, next year that we expect to validate at the ISS, we will incorporate rad hard electronics, and we hope actually that the resulting camera can be used in deep space.
Thank you, Raphael. And last but not least, Yona, anything more to add on trying to operate outside of LEO?
Maybe just a small comment. I already mentioned that for our mission, it doesn't really make sense, at least for the meteor observation part. We are also planning on using a dust sensor, which would be suitable to be used in outer space. And we already have some missions planned at our institute to do that. But regarding the camera and the meteor observation, all of our hardware is not suitable to be used outside LEO orbit. So it consists to a large part from commercial of the shelf parts, so it's not useful for outside the LEO orbit.
Thank you, Yona. Appreciate everyone responding to that. So let's see, going back to the Q&A. So this question is for Rico on CubeSat TOF. What is the energy range of the neutrons and ions that the CubeSat TOF can measure?
We can really go all the way from thermal energies, from 25 milli eV, which we would like to measure in thermal or in vacuum chambers, for example, during a deep atmospheric composition analysis, all the way up to 10-ish kilometers per second, let's say this way. Yeah.
Thank you. Let's see, question for Raphael. What is the material used to fabricate your mirrors and lenses?
Yes, so we have explored several. We started with BK7 rad hard, and now we're moving into Fuse Silica, also rad hard, that provides a very, very simple, easy to manufacture optical components, and also broadens the number of manufacturers that we have both in this country and in Europe.
Great, thank you. And let's see, for Andre, what fast steering mirror are you using? Can you give us a little bit more details on that?
Yeah, sure. So for Click Air, we're using 3mm aluminum MEMS mirrors from Miracle Technologies, which I think are the smallest package commercially available FSMs on the market right now.
Thank you, Andre. Let's see, another question for Raphael. Do you apply your onboard process? Are you applying your onboard processing for the machine learning algorithms, or is that more a ground operation? Can you give us a little more details there?
Yes, we actually have both, because we generate a huge amount of data at a very fast rate. We take images with these two-dimensional detectors every 0.2 milliseconds. So we need to do major image processing that will be able to combine the images on board, and then we'll be able to complete the final stage of the super resolution on the ground. But it is absolutely essential in our observational strategy to do the first part of the super resolution using these very sophisticated image processors on board.
Thank you, Raphael. Let's see. This one is for, I believe, Rico. Yes, for CubeSat TOF. Does the instrument make crosswind measurements?
We have an entrance angle for the ion source at about 5 to 15 degrees, and therefore we will see some composition variations, of course, while measuring it, but it's not optimized for that purpose.
Thank you, Rico. Let's see, another question for Raphael. Outgassing is a common problem in optics for space. Was that a major problem for you, and how did you overcome it? And I guess I had a follow-on question, just because since your payload's on the ISS, I've been there where something goes to ISS, and man, the requirements because of the human space program is really, really challenging. And just curious if you had any comments there on challenges getting your payload up there.
Yeah, the truth is that we did major testing campaign for over 3 years. And in fact, we worked with the 3 main space agencies, JAXA, NASA, and ESA. So the controls were very, very severe. We learned quite a lot in the process, and we subjected our optomechanics to various cycles in thermal vacuum chamber. And the truth is that we never had any major problem, neither with the coatings or the outgassing of the optics or the materials of the paint that we use then for the mechanics. And we were extremely pleased of working with NASA, JAXA, and ESA, and the success of the IOD in the ISS.
Thank you. Thank you very much.
Thank you.
Yeah. Okay, let's see. Let me actually do another round robin here for you guys. So I guess, yeah, maybe this will take us to the end in case we get any more. So what does the future hold for all of you? You know, hopefully with successful missions and instruments and science data, what's the long-term plan for your science objectives? So how about Yona?
Oh, okay, that took me by surprise. Yeah, that's a good question. So we certainly hope to get the proper funding to actually start our mission. We are, in the meanwhile, trying to keep working on it. And the goal would be to get a lot of data on the trajectory of meteors and determine maybe the parent comet of some meteor showers, or maybe combine our data with ground-based observations. So that would be a great goal.
Thank you. How about Robert for HiTi?
Yeah, really. You know, so I've been doing thermal remote sensing of the Earth for 25 years, and I've always been limited to Landsat class and ASTER class spectral resolution. I've never really been able to do any spectroscopy. We've yet to image the Earth. We've had V-square imaging spectrometers, and people have learned so much. Ideally, we can demonstrate HiTi, have more of them. Of course, then cross-calibration and intercalibration is an issue. But to provide scientists with frequent high spectral resolution, high spatial resolution thermal infrared data to study the chemistry of Earth's surface and atmosphere, it would be a new data set.
Thank you, Robert. Raphael.
Yes, so we're now working on the second flight model that we have to deliver to NASA this fall. It will be launched a year from now to the ISS to demonstrate the multispectrality and the agility. And then we are now working on the next mission on board the microsatellite that it will be launched in 2022. So it's been kind of busy over here in these days.
Yes, it sounds like it. Rico.
So the next years, I will be hopefully very busy with the upcoming CHESS mission I was talking about before. But it's really about bringing this instrument to other exospheres as well. Because, for example, we know more about Mars and Venus exosphere than we know about Earth, and that's why we need to measure Earth first, but also go there and do the same measurements so that we can say something about how our atmosphere has evolved over the time.
Thank you, Rico. Let's see, Andre.
Yeah, so Click A is actually just the very first step in our roadmap. We're already working hard on our follow-up mission, Click B and C, which will use much narrower laser beams and do inter-satellite links between two CubeSats, as well as precision ranging, which will enable navigation without GPS on orbit for swarms. And we're also branching into multiple different areas, for example, quantum key distribution from CubeSats. We have a new collaboration working on that. We're working on a hemispherical laser comm terminal, which will have a very high field of view, and also further miniaturizing these optical transceivers. So the future is looking very exciting.
Great, thank you very much, Andre. Simone.
Yes, we are currently working with in a couple of projects to provide the navigation and communication service to the Mars and Moon environment. So we are trying to customize our platform to provide this kind of service for the communication and navigation service on outer planet. Sorry.
Thank you, Simone. And John.
Okay, so I'm going to focus my answer on formation flying with diffractive optics, as opposed to going through the entire field X-ray gamma ray astronomy. No, so the whole point of doing this using precision or a high angular resolution measurements using diffractive optics and formation flying has been an ongoing exercise. I've been working on this for a while. I think with the advent of small sats and the potential for rideshare opportunities has really increased the potential for doing something like this. And so right now we are, as a matter of fact, yesterday I made a presentation in front of astrophysics at NASA, video astrophysics at NASA, to see potentially that this could be a supported mission for a mission of opportunity coming up for the next Explorers call. So that's what we're looking forward to in the near term. I think in principle, this technique, people have looked at using it for heliophysics, say for imaging X-rays from solar flares. And so the potential is there not only in astrophysics, but for other disciplines also.
Great, thank you so much, John. All right, well, I want to thank all of our presenters and all of the participants for bringing in your great questions. And I think now I'm gonna hand it over to Chuck to close us out.
Oh, okay, thank you. You know, I think we should give everyone a round of applause. I can hear the, you know, hundreds of people in the audience all clapping. We've had a great panel here, fantastic set of papers. I've been really impressed with them, and I encourage you in the audience to go out to the website and you know, look up on the on-demand, and if you haven't seen them, look at them again and replay them. Shannon, thank you for running a wonderful panel for us. It's been outstanding. And I think with that, we're done. Thank you for attending the webinar.